Okay, let's unpack this. I want you to just close your eyes for a moment. Let's really use your other senses to set a scene here.
Oh, I like this. We're going for a full sensory immersion right out of the gate. It really anchors the danger we're about to talk about.
We have to, because fire is so immediate, so terrifying. So imagine you smell that really specific, sharp, acrid smoke.
Yeah, not like a campfire.
No, no, not at all. It's that like metallic chemical smell of something synthetic going very, very wrong and fast.
You can feel the heat, too.
Yeah.
Even from a distance.
You feel that instant visceral heat on your face.
Yeah.
The air starts to shimmer and distort above the flicker, and then that split-second panic hit.
Right. That fight or flight moment.
And your instinct is just to grab the nearest tool.
Yeah.
The heavy red chemical canister, or maybe a bucket of water.
And you know whatever you grab is going to cause some kind of collateral damage. Water everywhere. That awful powder.
Exactly. But here's the twist. This is the intervention we're talking about today. Instead of a wet splash or that awful, blinding chemical hiss, a sound begins.
Okay.
And it's not a siren. It's not a high-pitched alarm. It's deep. It's heavy. And it's rhythmic. It's this low-frequency thrum.
Like a subwoofer.
Like the kind of massive subwoofer from a stadium concert has just been wheeled right into your kitchen.
So a bass drop that you feel in your chest, not just here with your ears. It's like physically vibrating the air around you.
The air itself visibly shakes, and the flame, which was just this beautiful, terrible destroyer seconds ago, starts to sway violently. It's almost dancing to this unseen beat.
It's stretching. It's reaching.
Yeah, it's desperately trying to maintain its shape against this invisible physical pressure.
And that pressure is physically disrupting the most critical part of the combustion process.
It's being silenced. And then just abruptly.
Yeah.
Without any toxic residue, without a splash of water ruining your electronics, without a chemical cloud, the flame is just gone. It wasn't smothered, it wasn't drowned, it wasn't chemically interrupted, it was simply defeated by physics.
And that right there, that is the mystery we are diving into. This deep dive is all about the revolutionary research that treats fire not just as, a chemical reaction, but as a system that can be precisely disrupted by acoustics.
This is the incredible, clean, and honestly surprisingly musical story of sound wave fire suppression. We're going to show you how a physics-based approach can provide a shortcut to safety, solving problems that chemicals and water just can't touch.
Yeah. So before we get into the rock and roll science of how you use bass to blast a blaze, we have to establish the stakes. I mean, they are enormous.
They really are.
What makes traditional methods so deeply flawed that we're now looking at specialized subwoofers for an answer?
Well, it really comes down to a few things. Speed, how well it works on different types of fuel, and crucially, secondary damage.
Right. Fire is just one of the most serious disasters threatening us. We're talking about massive destruction of forests, buildings, critical machinery, all within minutes. That rapid timeline means early detection and immediate intervention are everything.
But our current systems often fail in at least one of those areas.
They do. And this isn't just an occasional problem. Globally, it's an industrial-scale disaster every single year.
You found some stats on this, didn't you?
I did. We looked at the data from a 2020 census. It compiled info across 48 countries, so about 3.3 billion people. Fire departments complete around 70 million missions annually.
Wait, what? 70 million?
70 million emergency responses. And that resulted in over 20,700 fatalities and more than 70,000 injuries.
That is staggering.
It is. For every 100 reported fires, you get about half a fatality and almost 2 injuries. The societal cost, the economic damage, the human toll. It's just immense.
And even when the conventional methods do work, they're attacking that classic fire triangle, right? Heat, fuel, oxygen. But the attack itself often creates a secondary catastrophe.
That is the core issue. Let's break down the drawbacks. First, chemical extinguishers, the dry powder ones.
The red cans we all have under the sink.
Exactly. They rely on compounds like monoammonium phosphate or potassium bicarbonate. They work by coating the fuel with this thin, non-flammable layer of dust.
So it creates a physical barrier to separate the fuel from the oxygen.
Yes, but that barrier is the problem. It leaves behind a highly corrosive and toxic residue. If you discharge one of those extinguishers in a data center or near historical documents,
disaster.
Total disaster. The resulting dust is sticky, it's highly acidic, and it can just irreparably ruin sensitive electronics, archival papers, fine art. The cleanup is expensive, difficult, sometimes impossible.
So you trade a fire problem for a corrosive waste problem.
You've got it. And the disposal adds another layer. When these extinguishers are used or expire, they're classified as hazardous waste because of the chemicals. You need specialized handling just to get rid of the empty can.
And didn't we already ban the really good chemical agents?
We did. The really effective clean ones, like Halon 1301, were banned under the Montreal Protocol because they were destroying the ozone layer. Right. So, we banned the clean, efficient stuff, and now we're left with the corrosive, messy solutions.
Which means the global search for a clean, non-toxic alternative isn't just about making things better. It's about plugging this massive regulatory and environmental gap.
Absolutely.
Yeah.
And then there's water. We think of water as the universal fire killer, but it has severe, predictable limitations.
The first one that comes to mind is always electronics.
That's the big one. Water is incredibly damaging in any area with critical infrastructure. Server rooms, electrical substations, automated manufacturing lines, hospitals. A simple water sprinkler system can cause hundreds of thousands of dollars in damage, even if it puts the fire out instantly.
Right.
But even beyond electronics, water is fundamentally useless on many classes of liquid fuels. Things like gasoline, kerosene, certain solvents.
Why is that still a problem? It's the density issue, right? Water is heavier.
Precisely. Water is denser and therefore heavier than most of those fuels. When you spray it on, the water sinks immediately beneath the burning liquid.
So it loses its ability to suffocate the fire.
It does. Even worse, instead of smothering the fire, the water can actually spread the burning fuel across a larger surface area. It can turn a contained fire into a much larger moving disaster.
So water fails on liquid fuels, and chemicals leave toxic residue and holes in the ozone. And speaking of new threats, how do these conventional methods handle the new, frankly terrifying challenge of lithium-ion battery fire? Thermal runaway.
That is the ultimate villain of modern firefighting. Every electric vehicle, every large energy storage system, every laptop, they all rely on these batteries.
And thermal runaway is this chain reaction inside the battery itself, isn't it?
It is. It starts with a rapid, uncontrolled temperature rise inside the cell. It releases these volatile, flammable gases. And get this, it even releases its own internal oxidant.
Hold on. So if the battery is making its own oxidant, you can't starve the fire of oxygen. It doesn't need air from the outside to keep burning inside the cell.
You've nailed it. It creates a massive challenge. You're fighting an internal, self-sustaining chemical process. Conventional systems, whether it's water or dry chemicals, they're designed to interact with the surface of a fire.
They can't get inside the battery casing?
They can't penetrate it to stop the internal chain reaction. You might knock down the flames you can see with foam, but the cell is still heating up, and reignition is almost guaranteed moments later.
That sounds almost apocalyptic. If it's feeding itself and reigniting, the only thing we can do now is just pour massive amounts of water on it for hours, right? Just to cool the whole thing down.
Incredibly inefficient. And it creates the water damage problem all over again, but on a massive scale. So the search for a clean, non-toxic, reusable, and, universally effective method isn't academic anymore. It's a necessary engineering pursuit. We need something that uses physics, not chemistry, to break that fuel supply cycle.
All right, so now we get to go from the problem to the solution, which honestly, it feels like a great adventure story. And here's where it gets really interesting, because the idea of fighting fire with sound, it's not just some new theoretical thing. It actually started in military R&D.
That's the origin story, yeah. The concept was born in these high-risk, enclosed environments. So back around 2012, DARPA, the Defense Advanced Research Projects Agency, they were experimenting with sound suppression.
DARPA, of course.
Of course. And they were focused on these confined spaces like military aircraft and submarines. In those places, you can't just flood the area with foam. And critically, you can't deplete the oxygen because, that would endanger the crew. They needed something non-contact, something safe.
So the military does the initial work, proves the concept is, pardon the pun, sound. But it took a couple of college students to take that expensive theoretical principle and turn it into something practical and cheap.
Exactly. Enter our protagonists, Seth Robertson and Via Tran. They were electrical engineering undergrads at George Mason University back in 2015. They built the first functioning, low-cost prototype using commercially available parts.
I love that origin story because it always highlights the accidental nature of discovery. They started experimenting, and their first assumptions were based purely on brute force, weren't they?
Totally wrong assumptions. Yeah. They started out thinking bigger speaker, higher pitch, more sheer intensity. They assumed they needed these massive high-pitched waves to physically knock the flame out, just blow it out like a gust of wind.
But the flame didn't care about screaming sound.
Not at all. They learned really quickly that the magic ingredient wasn't screaming high frequencies. It was the low-frequency bass, that deep, resonant thump-thump bass in hip-hop that did the trick. They realized sound waves weren't about brute force wind. They were about rhythmic, precise disruption.
Okay, let's deploy the analogy engine. Let's dive deep into this mechanism because this is the core of the whole deep dive. How does bass, that low thrum, actually kill the fire? We're talking about acoustic streaming and airflow disruption.
Absolutely. So think of sound waves as these longitudinal pressure waves. They travel by creating these alternating zones of high pressure and low pressure as they push the air molecules around. The key with low frequency is that those pressure cycles are slower, which means the speaker membrane pushes the air molecules with greater displacement. They physically move farther with each cycle.
All right, let's use the analogy that worked so well in the source material, but let's really expand on it. Let's forget the fire triangle for a second and just look at the flame. Imagine the flame is like a busy food truck.
Okay, I'm with you.
It's serving vaporized gas. That's the fuel to waiting customers, who are the oxygen molecules. And this is all happening right at the edge of the flame, the boundary layer. That constant, smooth supply cycle is what keeps the fire going.
Perfect visual. The speed of the transaction at that window is everything.
So the low-frequency sound wave acts like an aggressive, rhythmic bouncer who just starts violently shaking the entire crowd. The sound doesn't put the fire out chemically, it doesn't remove the fuel. Instead, it physically displaces the air and the oxygen molecules, preventing them from mixing smoothly with the fuel. It literally stretches the flame away from the fuel surface.
So it breaks the fuel flame supply cycle.
Yeah.
The food truck customers can't get close enough to the window to place their order, so the whole supply chain just collapses.
Exactly.
And that displacement mechanism, that shaking and separating, that's the key concept. It's called acoustic streaming. It's a net, steady flow of air generated by the constant pumping of the speaker that physically stretches the flame until it's pulled completely away from the fuel source. It's not just vibrating the air, it's pushing it out of the way.
So we have the core principle. But as the students found out pretty fast, you can't just point a regular subwoofer at a fire and hope for the best. The system needs to be precise.
It absolutely needs precision.
Yeah.
Which brings us to the crucial component of this weapon system, the collimator.
The what?
The collimator. Sometimes it's called a vortex cannon, which sounds cooler. The basic setup has a signal generator for the frequency, an amplifier for the decibels, and a subwoofer designed for low-frequency effects, or LFE, usually in the 20 to 100 hertz range.
And without this collimator, all that precious bass energy just scatters harmlessly across the room.
Exactly. Sound waves naturally dissipate. They spread out as they travel. The early research showed that any experiments without the collimator just failed because the energy density was way too low by the time it reached the flame.
So the collimator is a tube, right, attached to the speaker.
It's a conical or cylindrical tube attached to the subwoofer, and its only purpose is to focus that powerful acoustic beam directly toward the base of the fire.
Okay, analogy time again. If the sound is the bouncer shaking the crowd, what's the collimator doing?
The collimator is the traffic controller with a megaphone. It doesn't let that traffic congestion of vibrating air molecules just wander off aimlessly. It forces them into a narrow path, channeling and directing that energy to slam right into the fuel-oxygen meeting point with focused force.
And the physical shape of that traffic controller matters a lot. The source material mentioned a specific conical design. Why is that taper so important?
It's all physics. It relates back to fluid dynamics, something called Bernoulli's theorem. When you force a fluid, and air acts like a fluid here through a converging pipe, the velocity of that fluid increases dramatically.
Okay.
So simulation studies confirm that using a conical design like one patent specified a 1:3 taper, meaning the length is 3 times the exit diameter, that significantly improves efficiency.
So by forcing the sound wave energy through that narrow cone, they're speeding up the acoustic pressure pulse.
That's it. Researchers found that when they reduced the exit diameter by 50% compared to the speaker size, they increased the acoustic velocity by an incredible 155%. That conical shape channels the energy, just like putting your thumb over a garden hose speeds up the water stream. That dramatic velocity increase concentrates the disruptive force exactly where it needs to be. So the early prototypes proved the principle worked, but turning a student project into, a viable technology that required massive industrialized data collection and precision engineering. This is where the scientists at Selcuk University took over with this exhaustive data quest.
Right. This is where we stop guessing and start calculating the exact recipes. We need to know the optimal distance, the perfect decibel level, and the specific frequency for every possible fuel.
That's exactly right. They went deep into optimization. These researchers conducted an astonishing 17,442 experiments.
Wait, 17,000?
17,442. Imagine the sheer dedication required to set up and measure 17,000 individual fires.
That's an industrial scale of discovery. I can't even imagine the time those poor grad students spent lighting and then silencing tiny fires. But managing all that complexity, fuel type versus frequency versus distance, all influencing each other, that must be a complete nightmare for a human to analyze.
It is, which is why they turned to the most effective decision maker available, machine learning.
AI.
Yep. They used advanced AI models specifically because the variables are so interconnected. They measured 6 key features in all 17,442 tests: the fuel type gasoline, kerosene, thinner, LPG, the flame size, the decibel level, the frequency, the airflow, and the distance to the flame.
Let's just simplify the AI's role here for a second. What were these models actually designed to do?
Well, they served as a decision support system. The AI's mission was simple. Given these 6 inputs, predict with super high accuracy whether a flame would be extinguished or not. They use one called the CN2 rule, which is great because it generates these really clear if-then statements.
Oh, so it's not a black box. It tells you why it made the decision.
Exactly. It'll say something like, if the frequency is 53 hertz and the distance is less than 0.6 meters, then the extinction probability is 99%. It gives you the rules.
That's fascinating.
And they used another called a stacking model, which combines multiple types of models to get peak accuracy. And the results, they were phenomenal. The basic model hit 97% accuracy, but that refined CN2 rule model hit an unbelievable success rate of 99.91%.
Seriously, a fire system that knows with 99.91% certainty if it's going to work before it even deploys? That's not a prototype. That's an intelligent, almost infallible safety system. The certainty is terrifyingly useful.
That certainty is the key to automation. It means we've successfully translated the art of firefighting into an applied science with predictable outcomes.
So, once the AI processed all that data, what did it tell us about the magic frequency? What did those 17,000 tests point to?
The data consistently confirmed what the students found. Frequency is king, and low frequencies are the most effective. They produce the largest particle displacement in the air, allowing that acoustic streaming mechanism to work best.
Higher frequencies just don't move enough air.
Exactly. They create too little displacement to effectively separate the oxygen from the fuel.
Give us the numbers on the sweet spot.
For liquid fuels, so gasoline, kerosene, thinner, the effective extinguishing range was consistently low, mostly 10 to 50 hertz at close range, about 10 to 100 centimeters. For LPG, it was a bit tighter, between 10 and 45 hertz.
And we saw this optimized range confirmed in the small-scale mobile prototypes, didn't we? That's the real-world validation.
It is. The unmanned vehicle prototype found an optimal operating range of 50 to 60 hertz at a distance of 0.6 meters. And importantly, it achieved an incredibly rapid response time of under 3 seconds. In another liquid fuel test, the fastest extinction time was achieved specifically at 53 hertz.
Wow.
So this consistency proves that the base isn't just effective, it's optimal.
But to highlight how crucial that focusing mechanism, the collimator, is, what happens if you try to put out a fire in open space without that focus sound? What does sheer raw volume require?
Without focused direction, you need absolutely monumental, dangerous power. Extinguishing a simple candle flame in free space required a peak acoustic overpressure of 191 decibels.
Wait a minute, 191 dB. We need to put that into context. Sustained human hearing pain starts around 120 or 130 dB. A Saturn V rocket launch is about 180 dB.
Yeah.
So that's a noise level that is medically dangerous just to put out a candle.
It's an extreme, unacceptable level for any real-world application. That data point is the proof of why the research immediately shifted away from sheer volume and toward precision engineering and focusing. The goal isn't to blast the whole room with deafening sound, but to deliver focused, lower decibel disruption to a single point.
And this brings us back to that crucial distinction you made earlier between simple oscillation and acoustic streaming. Why does the data show that streaming is the dominant mechanism?
Right. This is the difference between shaking the air and pushing the air. If the air molecules only oscillate, if they just vibrate back and forth really fast at a high frequency, they're shaking the fuel-oxygen boundary, but they aren't pushing the oxygen out of it completely.
It's like shaking a screen door really fast, but air is still getting through.
Precisely. The moment the sound stops, the molecules rush back in and the fire can reignite. Acoustic streaming, caused by that low-frequency pumping, creates a net, steady flow. It's a continuous, focused push of air away from the fuel source. It stretches the flame until the vapor can't maintain combustion anymore. The data confirmed its success came from systems designed to maximize that streaming effect. It's about effective displacement, not frantic vibration.
So if 191 decibels of raw power is wildly impractical, but a focused, low-frequency blast of 50 to 60 hertz through a collimator works in under 3 seconds, what does this all mean for the future of fire defense? So what does this all mean?
It means we are looking at a huge environmental and safety victory that could redefine how we secure critical assets. We have a non-invasive solution that is non-harmful to people and nature, leaves absolutely no toxic residue, and can be used over and over again.
And that non-residue factor is just massive for specific sensitive locations where traditional methods cause so much collateral damage.
Yeah.
Where does this technology immediately become essential?
Well, think about the places that suffer the most secondary damage. Data centers and server rooms are the obvious ones.
Yeah.
Water or chemicals instantly destroy millions of dollars of equipment.
Right.
But it goes so far beyond that. Consider historical and cultural sites, museums, libraries, archives, places where the contents antique manuscripts, delicate fabrics, irreplaceable artwork can't tolerate water or corrosive powders. An acoustic system protects the artifact while extinguishing the threat.
It's the ultimate clean room solution for fire. You put out the fire, and immediately you can assess the damage without a massive cleanup operation getting in the way.
Exactly. And there's a huge logistical advantage in the reusability. A chemical extinguisher is one and done. Once you pull that pin, you have to dispose of the canister and buy a new one. An acoustic system, powered electrically, can be tested, maintained, and deployed infinitely, as long as it has power.
The mobility factor is also a major advantage, right? Especially when we combine this with modern robotics and automation, we can move this from a lab into the real world.
Absolutely. The compact nature of the module makes the technology perfect for smart, autonomous systems. We already have acoustic modules mounted onto unmanned ground vehicles, or UGVs. Researchers have shown they can identify a fire in a pan and put it out from a meter away in under 5 seconds with a mobile system like that.
Which keeps people safe.
Exactly. And the next logical leap is putting that power in the air. Drone platforms have to be a major focus.
Oh, yeah.
The potential for UAVs, for drones, is just massive, and it's cited all over the research. Imagine rapid response drone units that could quickly access the site of a fire, whether it's in a high-rise building or a hard-to-reach forest area, without putting human firefighters at risk. The drone uses computer vision to track the fire, calculates the optimal acoustic recipe, and deploys the focused base wave from above.
And that brings us full circle back to the power of the AI. With those models hitting 99.91% accuracy, the brain of that intelligent firefighter could be fully autonomous and instantaneous. It removes that, decision time required during panic.
It's the ultimate closed-loop system for rapid response. The computer vision instantly identifies the fuel type. Say it sees a liquid fuel fire and it measures the distance. The AI model instantly calculates the optimal frequency, maybe 53 hertz, and the precise decibel level required. The acoustic module deploys the perfect sound recipe, all automatically, in milliseconds. It takes human error and hesitation completely out of the equation.
That level of instantaneous, customized precision it's revolutionary. And the research isn't stopping at just putting fires out. There are advanced strategies being explored, including, prevention.
Yes, there are some really exciting frontiers. Some research is focusing on using extremely low-frequency sound, known as infrasound, sound below the range of human hearing, so under 20 hertz.
And that's not to extinguish a flame, but to stop it from even starting.
Potentially, yeah, to prevent ignition entirely. The idea is, if infrasound can disrupt the preliminary mixing of fuel vapor and oxygen effectively enough, it could create zones where combustion is chemically impossible. It could act as a preventative shield in high-risk areas.
Wow. And what about more practical near-term ideas, like hybrid systems?
That's a highly pragmatic approach. While acoustic suppression is powerful, if you need to tackle a larger fire, the decibel requirement goes up, and that raises potential noise hazards. So studies are suggesting combining acoustic waves with other methods, specifically water mist.
So you're still using water, but in a smarter way.
A much smarter way. The water mist is still clean, but the acoustic waves actually break the water droplets into much finer, more evenly dispersed particles. This enhances the overall cooling and smothering effect.
So the base wave helps the water work better.
It does. It can reduce the suppression time significantly, sometimes down to around 30 seconds for certain industrial fires, while requiring less raw acoustic power. It's about optimizing both speed and safety, proving that sound can be a powerful force multiplier.
This has been a true deep dive into applied physics. So, to review, we found that the secret to silencing fire isn't brute volume or screaming high pitch, but rather highly focused, low frequency bass. The sweet spot is consistently around 50 to 60 hertz, channeled through a conical collimator that dramatically increases the wave velocity.
And this whole process is driven by acoustic streaming, that steady net flow of air, which physically disrupts the fuel-oxygen boundary layer. It essentially pushes the flame off its critical supply cycle. And this has all been validated by massive data sets and AI models that can predict success with near-perfect accuracy.
The promise here is fire suppression that leaves zero toxic residue and causes zero secondary damage to electrical systems, electronics, or fragile historical materials. It's just ideal for autonomous deployment on UGVs and drones.
We started with the sheer terror and destructive power of fire, which, it's historically required us to use destructive or chemical-heavy methods to stop it. We learned about the limitations of water on liquid fuels, the toxicity of dry chemicals, and that existential self-feeding threat of thermal runaways in modern batteries.
But the research suggests that the future of fire defense may not be fought with materials at all, but simply countered with tailored physics. Instead of brute force or toxic compounds, we are using precision disruption and acoustic energy.
So imagine a future where the sound of heavy bass, that rhythmic, low thrum, means not a party starting but a fire ending, where safety comes from precise frequency control. The power to destroy is being countered not by an equal and opposite material force, but by the power to simply disrupt the physics of combustion itself.
And the final provocative thought is this. If we can tune a simple, low-frequency sound wave to break the physical chain reaction of something as fundamental and dangerous as fire so effectively, what other seemingly unstoppable or overwhelming forces in our world might be countered, not with new materials, but with an intelligent application of fundamental physics? That's the truly deep dive here, the realization that sometimes the simplest waves hold the most revolutionary power.